This is the first part of the Amazon EKS tutorial. Here we're going to create all necessary network components starting with VPC using Terraform. Terraform is widely adopted and is de facto standard in our industry for managing infrastructure. We'll start by creating 4 different subnets, 2 private and 2 public, in 2 different availability zones. EKS requires you to provide multiple subnets in at least 2 different availability zones. We'll use private subnets to deploy Kubernetes nodes and use public subnets to provision network and application load balancers. Later in the tutorial, we'll use both the native Ingress provided by the AWS Load Balancer controller as well as open source Nginx Ingress controller and secure it with a TLS certificate. We'll also cover all necessary subnet tags that must be present for the EKS to properly discover subnets. Then we'll create Internet Gateway and attach it to our VPC. It is used to provide internet access to any virtual machine that have a public IP address and located in public subnet. Then we'll create a NAT gateway and place it in one of the public subnets. It is used to translate private virtual machine IP addresses located in private subnets to a public one, and it allows internet access within private subnets. Then we'll create a public route table with a default route to the internet gateway. For example, when the destination IP address of the request is located inside the VPC, the main route is used, but when the destination IP address is outside of the VPC, the request will be routed using the default route. In this case, the Internet Gateway. We'll also create another private route table with a default route to NAT Gateway, which allows virtual machines with private IP addresses to reach the internet. For example, to download a Python package or access external API. And finally, we'll attach these route tables to our 4 subnets. That would be the scope of this section. A little bit about AWS Network and Terraform to get you started. You can clone my public GitHub repo to follow along. I would also suggest deleting all the Terraform files under Terraform folder and creating them with me from scratch. Now, personally, I don't like to use a lot of variables when I try to teach something. In production code, you would of course refactor and parameterize most of the values in the code. But anyway, let's define the most common parameters that we'll use in Terraform as local variables. First of all, we need to define environment variable. We frequently create multiple environments, such as development, staging, and production in a single AWS account. In order to do that, we need to use environment as a prefix for objects such as IAM roles, policies, and the EKS clusters themselves. Also, I use numbers to prefix Terraform files. It's intentional just to clarify the order in which you would create resources. In real code, you would not use such prefixes. Then we have the region where we want to create our infrastructure. When you create EKS cluster, it requires you to have multiple subnets in at least 2 different availability zones. You can think of availability zone as a separate data center, so this is done to improve your availability. If something happens in one zone, you would still have operational cluster. Then we have the EKS cluster name, which we'll also use as a prefix for IAM roles and policies, just in case we create multiple EKS clusters in the same AWS account. And finally, we need to specify EKS version. At this moment, 1.29 is the latest supported Kubernetes version in AWS. You can always check this page to find the latest version. Next, let's create a providers file. You can think of a provider as a set of functions specific to a cloud or open source project. Of course, we need to define AWS provider and specify the region. In this case, we use local variable region. Then we can define some constraints on the Terraform version and the provider itself. For example, at this moment, 5.49 is the latest version. Throughout the tutorial, we'll use 4 or 5 additional providers, such as Helm, TLS, and Kubernetes. If you create a module, the best practice is to define the version constraints for all of them. Next, let's create a VPC object using Terraform as well. You would define the seeder. The most important part is to come up with a seeder range that is large enough and will not clash with other VPCs or external networks in case you want to peer VPCs or use site-to-site VPN. Next, let's enable DNS support in the VPC. It is a requirement for some add-ons such as EFS CSI driver or even client VPN, so I would suggest keeping this enabled. And finally, we can define a tag with the environment prefix. Next, we need to create Internet Gateway. It is used to provide internet access to the public subnets. First, we need to attach it to the VPC and additionally add a name tag. Name tag, which starts with capital N, is a special tag that will be visible by default in AWS console. Now, let's create 4 subnets, 2 private and 2 public subnets in 2 different availability zones. First, let's define the private zone. Attach it to the VPC using resource reference. Define the seeder block. I like to use online seeder calculators to come up with the seeder ranges. They will show you how many IPs you have and the last usable IP address. Next is availability zone. This one is US East 2A. And we also need to create some tags. First, let's use environment prefix, type of the subnet and availability zone. Next, internal ELB is a special tag that is used by EKS to create private load balancers in case you want to expose your service internally within the VPC. And the last tag is optional but recommended if you decide to provision multiple EKS clusters in a single AWS account. This is EKS cluster name, and the value can be either owned or shared. Next, let's create another private subnet with a different seeder range and place this subnet in a different availability zone, US East 2B. Next, let's create a public subnet. Use the same VPC, provide the seeder range, and also place it in the first US East 2A availability zone. Now, some services and VMs may require public IP addresses, so let's enable this. If you create a virtual machine in the public subnet, AWS automatically assigns it a public IP address so that it can reach the internet. Even without this option, you can assign a public IP manually. Next, we need to define a few tags. The first one is the same, just a name tag. Then a slightly different ELB tag is very important. EKS will use it to discover subnets to create public load balancers. And the last is to establish a relationship with the EKS cluster. And finally, the last public subnet in the US East 2B availability zone. Just make sure that you use a different seeder range and zone. So far, we have created 4 subnets, but for now, they are neither public nor private. They don't have any default routes. Next, let's go ahead and create a NAT gateway. It is used to translate private virtual machine IP addresses into public ones to provide internet access to private subnets. But before we create the NAT, I would highly recommend allocating a static public IP manually. We'll use it in the NAT gateway. In the future, in case your clients require a webhook or something similar, you can easily provide and whitelist this IP address. Otherwise, it will be created and managed automatically by the NAT gateway. Also, make sure you place the NAT gateway in one of the public subnets with a default route to the internet gateway. We can also use depends on clause to wait until the internet gateway is created. The final step for this section is to create private and public route tables. First of all, let's create a private table. Define the seeder block that indicates the default route, which means if no other routes match the request, this route will be used. By the request, I mean the destination IP address. And as a gateway, let's use NAT. So in this case, if your application wants to send a request and the destination IP address is not within your VPC range, it will be routed outside of your VPC using the NAT gateway. And let's set a name tag. Next, let's create a public route table. The only difference here is that we use Internet Gateway as a default route. And finally, we need to associate these 2 route tables with our 4 subnets. First, let's assign the private route table to the first private subnet. Then assign it to the second private subnet. Keep in mind, some may recommend creating multiple NAT gateways in different availability zones and creating multiple private route tables. I have never found this particularly useful in real environments. Next, assign the public route table to the two public subnets. That's pretty much all for the creation of a VPC from scratch. Let's switch to the Terraform directory and initialize the state. Terraform will download all the providers used in the code and initialize the local state file. In production, you would use a remote state in S3 bucket. I have a video on best practices if you're interested. Now, just because in the following section I'll show you how to add additional users and IAM roles to the EKS cluster, let me show you from scratch how to initialize your first default local profile. For this tutorial, I'll be using my own user that is already placed in admin group, but I still need to generate access key. Let's go to security credentials and click on create access key. Now, just to avoid any warnings, let's select other for the purpose. And here we go, we have the credentials. I'll delete all the users and keys after this tutorial, so you'll need to generate your own. Now, to create the default profile, you need to run AWS configure, enter the key ID and the secret access key. You can leave other settings empty. Alright, now AWS Terraform provider will use this default profile. You can use other authentication methods. Generally, the best practice is not to use authentication method with long-lived credentials and instead use IAM roles with short-lived credential tokens. But that's out of scope of this tutorial. So these are your default credentials and the default profile. Alright, let's go ahead and apply Terraform. It'll take maybe 2 or 3 minutes to create VPC and subnets. Let me show you in the console what we have so far. We have a staging main VPC, 4 subnets, 2 private and 2 public. By the way, you may have a default VPC which is used only in tutorials and it's never used in real environments, so you can safely delete the default VPC and all corresponding subnets. It'll make your life easier. And just in case you want it back, it's very easy to create a default VPC with one single click. Now, for example, the private subnet has a default route to the NAT gateway, and the public subnet has a default route to the internet gateway. We also have 2 route tables, an internet gateway and the NAT gateway. I have only one. The first one is from previous tutorial. Alright, that's pretty much all for this first section. This is the second part of Amazon EKS tutorial. Before we start creating EKS itself, let's go over the main Kubernetes components. It's going to be important later in terms of what IAM permissions we need to grant to EKS. First of all, we have etcd database. Kubernetes uses it to store all its state, such as deployment specifications, how many replicas of each pod it needs to run, and stuff like that. So it's important to regularly backup etcd and be prepared to recover it in case something happens to it. Then we have the scheduler. Its main job is to watch for newly created pods and assign them to the nodes based on available CPU and memory and pod requests. Next, we have the controller manager. It combines many different controllers. It's basically a reconciliation loop where controllers watch for the current state and ensure it matches the desired state. For example, if instead of 4 pods, only 3 pods are running, controllers will make sure that the current state matches the desired state. Then we have the legacy cloud manager. It's part of the Kubernetes source code and only receives security and bug fixes at this point. Originally, it was created to integrate with different clouds such as AWS, GCP, Azure, and others. For example, when you create a service of type load balancer based on the cloud where Kubernetes is running, it will make necessary API calls, and in case of AWS, it would create a classic load balancer. As you can see, this component would require additional specific IAM permissions to create load balancers. But a while ago, cloud providers started to develop their own external controllers to deal with cloud-specific logic. For example, later in the tutorial, we'll install AWS Load Balancer controller to create load balancers and ingresses. Because it's not part of Kubernetes source code, it's much easier to introduce new features and release bug fixes, and it would require a dedicated IAM role to interact with AWS. Now, in order to interact with all these components, Kubernetes has additional stateless API server. It includes authentication and authorization. So if you want to create a deployment object and run kubectl apply, it will take your YAML file and send API request with that payload to the API server. On the other hand, we have Kubernetes nodes. We have kubelet, which is responsible for running containers defined in the pod spec, and kuproxy, which is a network proxy that allows communication to your pods from the network inside or outside of your Kubernetes cluster. In production, we want to have a highly available cluster. For example, if something happens to etcd server, we still have others that can serve the requests. We used to use kops before EKS to provision Kubernetes clusters, but you would still have to manually run kops CLI to maintain the cluster. Now, we can delegate the management of the control plane to AWS. The managed service is called EKS. At this time, it's only 10 cents per hour per cluster. I think it's a great deal, and I would not think twice to use EKS instead of managing my clusters using kops. Also, with kops, we had to use a virtual network, and in terms of access management, it was a nightmare. Without using additional tools like DEX, you have to attach all IAM policies to the Kubernetes nodes, and all applications would get the same access, which is not good at all. Now, since EKS is tightly integrated with AWS services, especially with IAM, Identity and Access Management, let's briefly go over some terminology. Like many other AWS services that interact with other AWS services, such as EC2 and load balancers, EKS requires some permissions. In order to grant permissions to AWS service, we create IAM role and define the trust policy. This is usually done with a principal property in IAM role. In this case, we create IAM role that can only be used by EKS service and nothing else. IAM role is similar to IAM user. You define what that entity can and cannot do in AWS. The difference is that IAM user is usually uniquely associated with one person, but a role is intended to be assumed by anyone who needs it and has permission to assume it. Also, IAM role compared to IAM user doesn't have standard long-term credentials, such as a password or access keys associated with it. Instead, when you assume a role, it provides you with a temporary security credentials for your role session. That's why even to run Terraform, IAM role is preferred due to the short-lived token. So if the token is compromised, it can only be used for a very short time, usually 1 hour. Alright, next we need to attach permissions to that role. You can use the one that AWS manages for the EKS service. It's called Amazon EKS Cluster Policy. In this tutorial, we will be using this managed policy. However, this policy assumes that you would use a legacy provider that additionally requires load balancing permissions. So it's like half of the policy is dedicated only to that legacy provider. In the following sections, we will install AWS Load Balancer controller that would take on that responsibility, and for that we will create another separate role. For now, we can use this managed policy, but AWS provides a minimum set of permissions if you want to restrict it to only the core EKS functionality. Next, let's talk about what kind of permissions Kubernetes workers would require. The first one provides the core EC2 functionality permissions. It's called Amazon EKS Worker Node Policy. It also allows running Pod Identity Agent, which is used to grant granular access to your application. For example, you can grant your application read and write access to specific S3 bucket. This is the third iteration of access management. Before Pod Identities, we had to use OpenID Connect provider and IAM roles for service accounts. I cover it in a section dedicated to all these three methods of authentication with hands-on examples. Next, we have to grant EKS access to modify IP address configuration on your EKS worker nodes. For example, when you create a pod, the IP is allocated from the secondary IP address range assigned to the worker node. So we're not using virtual networks such as Flannel or Calica anymore. You get native AWS IP addresses for each pod. Later, you'll see a benefit when we start creating load balancers and use IP mode to route traffic directly to the pod IP address. Before that, cloud providers had to use node ports behind the scenes when you created services of type load balancer. Now it's direct. By reducing the number of network hops, we reduce the latency of the requests. And lastly, the Amazon EC2 Container Registry read-only IAM policy is used to grant EKS permissions to pull Docker images from the AWS managed container service called ECR. That's all the permissions for now. Let's go ahead and start creating Terraform resources. First, we'll start with the creation of the control plane itself. Take a note that we're using environment and EKS cluster name as a prefix for the IAM role in case you create multiple EKS clusters in a single account. Also, there are no strict naming standards like using camel case or snake case in AWS. Just pick one naming standard for yourself and keep using it throughout the whole Terraform code. In this case, we use a plain multi-line string. Later in the tutorial, we'll use JSON code built-in function. I'll show you different ways just in case you saw it in one of the examples on the internet and are familiar with it. The next step is to attach Amazon EKS Cluster policy to the IAM role that will be used by the EKS. The following Terraform resource is for EKS cluster itself. We'll use environment as a prefix as well in case you create multiple clusters in the same AWS account. Then we use the latest Kubernetes version supported by AWS. By the way, upgrades are as simple as updating the version and running Terraform apply. Next, we need to attach our IAM role to the EKS cluster. Then we need to configure networking settings. In the following tutorials, I'll show you how to create a fully private EKS cluster with client VPN and even private DNS that you can use for your Ingress and private services that you don't want to expose to the internet, like a Grafana dashboard with metrics. For now, we'll enable public EKS endpoint. You would still have your worker nodes deployed in private subnets without public IP addresses. So it's very safe, and perhaps you would create a fully private EKS cluster only if you have a specific requirement from the business or other stakeholders. Now, since we want to deploy worker nodes in private subnets, we need to specifically provide subnet IDs. As I mentioned before, those subnets must be in at least 2 different availability zones. Amazon EKS will create a cross-account elastic network interfaces in these subnets to allow communications between your worker nodes and the Kubernetes control plane. Next, we need to configure authentication. We used to have to manage access to EKS using Kubernetes auth config map in kube system namespace. It wasn't very convenient to manage existing config map in Kubernetes using Terraform resources. Finally, EKS team developed API that you can use to add users to your cluster. You can still use config map or even both, but I highly recommend using API for user management if you create a new cluster. In the next section, I'll cover how to add IAM users and IAM roles to access the cluster. Now, make sure that you also grant your Terraform user, which is used to create EKS cluster admin privileges. It is a requirement for us because we will use Terraform to deploy Helm charts and plain YAML resources. It says it defaults to true, but it's better to explicitly enable it in case the default change in the future, which would break your pipeline. And finally, let's explicitly depend on the attachment of permissions to the EKS IAM role. Next, let's create Kubernetes node group. Kubernetes uses them to run your applications. First of all, we need to create another IAM role for your worker nodes. For the trust relationship, you would put EC2 instead of EKS service. By the way, in the next section, I'll show you how to create IAM role with a trust policy that allows specific users to assume it. Now, we need to attach multiple IAM policies to the nodes. The first one is Amazon EKS Worker Node Policy. The second one, Amazon EKS CNI Policy to manage secondary IPs for the pods. And finally, you would attach Amazon EC2 Container Registry Read-Only Policy to pull your private Docker images from the ECR Container Registry. And the final object is the node group itself. Behind the scenes, it's managed as EC2 Autoscaling group. EKS generally has two types of groups. The first is a self-managed node group that you create using Terraform and templates manually. It is useful when you have specific requirements for the nodes. Basically, you create the node from scratch like you would install any necessary packages on your Linux machine using Packer. There are some limitations. For example, EKS would not drain the node when it upgrades, so you can still do it, but it's a semi-manual operation. Next, we have EKS Managed Node Group, which is what we will be using in this video. It's way easier to manage and upgrade because it's done automatically by the EKS control plane. And the third group is Fargate, which is a serverless service. When you create a pod, EKS will create a dedicated node for each pod. It's way easier to manage, but way more expensive and has some limitations like EBS volumes. I'll create a separate section on EKS Fargate. Alright, first we need to attach this node group to the EKS control plane. Then let's use the same version 129 for the nodes. Give it a name like general. Usually, you would have a different node groups. You may have CPU optimized node groups, memory optimized node groups, or even GPU node groups to run machine learning. In the cloud, it's common to have a separate spot node group, which is much cheaper, but AWS can take them away at any time, and your application must be able to tolerate such interruptions. They are frequently used for batch jobs and streaming jobs that in case of failure can start from the previous save point. Next, we need to attach the IAM role that we created earlier. Then we need to provide subnets for the nodes. In many tutorials, we frequently use subnets in multiple availability zones. But in real world, especially in large companies, if you have, for example, Kafka and hundreds of services that read and write to and from Kafka from different availability zones, it can be super expensive due to the data transfer costs between different zones. Sometimes those charges can even be more than the compute you use for the infrastructure. My point is that you don't necessarily have to create a highly available cluster by spreading nodes in different zones. I know many companies use a single zone. It's way cheaper in some cases, but there is a small chance of failure. It's up to you. Then we have the capacity type, which can be standard on demand or cheaper spot instances, and the type of instances. I'll create a dedicated tutorial on how to come up with the proper node size in the future. Then we have the scaling config. By itself, it will not be autoscaled. We need to deploy additional component called the Cluster Autoscaler. Here you define the minimum and maximum number of nodes, and the Cluster Autoscaler will adjust the desired size based on the load, like how many pending pods you have and their resource requirements. Next, we have update config, which is used for cluster upgrades. And finally, we have labels. We can use them in pod affinity and node selectors. There are some built-in labels derived from the node group names, but in practice, when you try to migrate applications from one node group to another with the same labels, it's much easier. So I would suggest using custom labels for affinity. We also have a depends on clause to wait until the IAM role is ready and all the policies are created and attached. Terraform resources also allow you to ignore certain attributes of the objects you're trying to create. For example, when we deploy Cluster Autoscaler, it will manage the desired size property of the autoscaling group, which will conflict with the Terraform state. So the solution is to ignore the desired size attribute after creating it. Alright, that's all Terraform for this section. Let's go ahead and run Terraform. It may take up to 15 minutes in worst case to create a cluster. Now, let me show you in AWS console what we have so far. So we have the staging demo EKS cluster. You can see some other attributes as well. At this point, the most important part to check if the user, in my case a Putra, was added as admin to the EKS cluster on the Kubernetes side. This ensures we can create and get any resources in Kubernetes. You may see a warning that we need to install EKS pod identity agent. I have an entire section covering that part. Also, let me show you that EKS node group is created as autoscaling group. You can see the autoscaling settings. The minimum and maximum are defined in Terraform, and the desired size property will be updated by the cluster autoscaler. I'll also include autoscaling with Carpentner and Keda in the playlist later on. Finally, let's make sure that EC2 instances are running in private subnets without public IP addresses. Now, it's time to connect to the cluster. First, we can check that we have the right user. So I used this one to create a cluster. Next, to connect to EKS, we need to update the local kubeconfig with the following command. You need the region and EKS cluster name. We'll use profiles in the next section. Now, a quick check to verify access. If we can get nodes, most likely we have admin privileges. And just to make sure that we have read-write access to everything, you can run the following command. I'll explain it in detail in the next section as well. If the answer is yes, it means you are admin in that cluster. That's all for this section. In the next section, I'll show you how to add IAM users and IAM roles to the EKS cluster, and we'll talk about best practices. This is the third part of Amazon EKS tutorial. Let's say you have created a development EKS Kubernetes cluster. If you used IAM user to create the EKS, only you have access to that cluster. It's very likely that you have other team members who would like to do something with that cluster. You may have other DevOps team members that would need admin privileges to maintain the cluster. You may also have, let's say, development team 1 that needs access to a specific namespace, like team 1 namespace. You could create a namespace resource quota. For example, this team can only use 10 CPU and 20 GB of memory and create a maximum of 12 pods. You create quotas to avoid any interference between teams. One team could use all the EKS resources, and if the other team tries to deploy, Sometimes pods will be in pending state, and you can be sure that they will blame you for the EKS cluster being broken. You could also have another development team, let's say team 2, that needs read and write access to another team 2 namespace for their development work. You can grant access to individual user, but the better approach would be to create a common IAM role for the team, assign all the permissions to that role, and allow team members to assume that role. Later, you may create a dedicated EKS cluster for the production environment. Typically, you would only grant read access for the developers for them to be able to debug if necessary. By using Airbag, you could also grant them only permissions to access the application logs in their namespaces. So there is a lot of flexibility in Airbag. Now, on the AWS side, we can use IAM users or IAM roles as objects that represent identities. On Kubernetes, for the identities, we can use Kubernetes service accounts, users, and Airbag groups. In this video, we'll map IAM user and in the second part, IAM role to a custom Airbag groups that would have different permissions. I have another tutorial that covers Airbag in detail if you want to learn how to grant your identities granular access within Kubernetes. For the first example, we'll use IAM user as well as IAM policy with a minimum set of permissions for that user. It will only allow updating the local Kubernetes config and connecting to the EKS cluster. On the Kubernetes side, we'll create a viewer role with read-only permissions to access certain objects from the core Kubernetes API, such as deployments and config maps. Then we'll use cluster role binding to bind this viewer Airbag role to a new myViewer Airbag group. And finally, in order to link IAM user with this Airbag group, we'll use EKS API instead of old deprecated auth config map. The best practice is not to use identities such as IAM users with long-term credentials. Instead, for the second part, we'll create IAM role and IAM policy that would grant that IAM role admin access to EKS on the AWS side. On the Kubernetes side, we cannot use built-in Airbag groups that start with system prefix. So we'll use the default cluster admin cluster role and bind it with our new myAdmin group. Next, we'll create a manager IAM user and additional IAM policy that would allow that user to assume the EKS admin IAM role. Finally, we'll bind that IAM role with Kubernetes myAdmin Airbag group using EKS API. First of all, let's go over Kubernetes Airbag part. Let's create a cluster role with read-only permissions for all namespaces. Those users will get, list, and watch permissions for objects like deployments and secrets. The star indicates the core API group. You can call this role reader or viewer, it's up to you. Now, we need to bind this role to some kind of Kubernetes entity. We can use users, Kubernetes service accounts, or like in this case, we can create myViewer Airbag group. I intentionally use different names to make it obvious in the next part which entity we will link with AWS IAM user. Besides the group, we need to specify which role we want to bind to this group. In this case, it's viewer. Let's go ahead and apply the role and binding. Next, we need IAM user to play with. You can create this user from the console, but I'll use Terraform to create the user and AWS console to generate the keys. However, you can do everything through the Terraform. First of all, let's use AWS IAM user Terraform resource to create a developer IAM user in AWS. Then we need to grant access to EKS in AWS to at least be able to update local Kubernetes config and connect to the cluster. This is the minimum requirement. This user won't be able to view workloads in AWS console, just connect to the EKS cluster. And of course, you can restrict it to a certain cluster only, for example, to only development EKS cluster. Next, we directly attach this policy to our user. The best practice, of course, is attach those permissions to IAM group and place the user in that group. Next, the most important part is to bind developer IAM user with Airbag myViewer group using EKS API. This part used to be managed through Kubernetes auth config map, but now it is deprecated, and this is the only recommended option. Alright, let's go ahead and apply Terraform. Now we have the developer user, and the next step is to generate security credentials for our user. It's pretty much the same as we did in the first section. The difference here is that we'll create a custom profile for that user. Let's run AWS configure and give this profile a name, developer. Copy access key ID as well as the secret access key. Next, let's make sure that we configured that profile correctly and can access AWS. You can see the IRN of the user is developer. The next step is to connect to EKS Cluster. It's pretty much the same command, just add profile developer. Most of the AWS CLI commands accept this flag. Now we can quickly check that the local Kubernetes config uses developer profile. You can see below the profile that was used to connect to EKS. Let's check if you have access to the cluster. If you remember, we created a custom cluster role for this user and bound it with the My Viewer group. So we should be able to get pods in all namespaces. kubectl has a subcommand that can help you to check access to Kubernetes. First, the verb is for the action, like get. Second, for the type of object, in this case, pod. So the answer is yes. Now, let's see if we can get nodes. We have the error since the viewer cluster role does not have permissions for global resources. We can use the same auth subcommand and get the no answer. Also, to check if the user has admin privileges, you use a star for the action and for the resource type. So the developer obviously doesn't have admin access. Next, we'll create another IAM user and IAM role and grant admin privileges in the cluster. Kubernetes ships with the default cluster admin role and group. However, the EKS API for managing access won't let us use the default group that starts with the system prefix. So we need to create our own admin group in Kubernetes. It's actually very easy. We'll use existing cluster admin role and bind it to our new My Admin group. Now, before we can apply this cluster binding, we need to switch to the previous user that created EKS cluster and has admin access. Just run update one more time without specifying the profile. It will use the default profile. Let's apply the binding and create My Admin airbag group. Next, we need to create a manager IAM user and role using Terraform. First, we need AWS account number for IAM role. You can hardcode it, but a better approach would be to use Terraform data resource to dynamically retrieve it. Next, we create IAM role that would get admin privileges inside the Kubernetes cluster, and you can share this role with anyone who needs it. There are a couple of ways to define trust relationship with users. One way is to create a role and use root as a principal. In this way, potentially all users in that AWS account will get access to that role. Next, we need to create IAM policy with admin access inside AWS account. So these permissions are granted on the AWS site. You can also grant additional permissions to view all EKS tabs. Next, we bind IAM role with those permissions. Alright, the next step is to create another IAM user and let that user assume this role. We'll also use Terraform to create the user and we'll generate keys manually. Keep in mind that when you decide to tear down the infrastructure, for example, to run Terraform destroy, first you would need to manually delete keys from AWS. Otherwise, Terraform won't be able to delete these users. Next, let's create IAM policy that would allow assuming EKS IAM admin role. It's very simple, we just use the IRN for that role under the resource. Next, we attach that policy to the user. Again, best practice is to create IAM group. Then we use EKS API and bind IAM role, in this case with My Admin airbag group inside Kubernetes. Alright, let's go ahead and apply it. Now we have a manager user and we need to generate security keys to create a local AWS profile. let's configure the manager profile, but we will not use it directly to access EKS. So keep watching. Copy the access key and the secret key. Now, this is important check if you can assume EKS admin IAM role. If you get temporary credentials back, it means you configured everything correctly. Now, we need to create another AWS profile manually. You can use any text editor. Right under the manager profile, let's create another one and call it EKS admin profile. That profile doesn't have any credentials. Instead, it will use the manager profile to assume this role and obtain a temporary session token. So we have EKS admin profile, IAM role, and manager source profile. Again, let's update Kubernetes config, but this time use EKS admin profile, not manager. Check if the correct profile is used. Try to get pods and check if you are admin in that cluster. And the answer is yes. Lastly, let's see what EKS tab in EKS shows. So we have EKS admin role bound to my admin and I'm user developer bound to my viewer airbag group. Don't forget to delete security keys manually from AWS console before running Terraform destroy and use IAM roles instead of binding a single IAM users to groups in Kubernetes. The next part will cover horizontal pod autoscaler and how to install the metrics server in EKS using Helm Terraform provider. This is the fourth part of Amazon EKS tutorial. In this section, we'll cover horizontal pod autoscaler and required components that you need to install to make it work. Usually, we would use CPU usage or memory usage metrics to decide when we need to scale up our application. The important part here is that when you create a deployment or stateful set, you must have the resource block defined. HPA will use a requests section to calculate CPU or memory usage of the pod, not the limits. So if you forget to define resources, your HPA object won't work, and if you describe it, you'll see unknown for the target. Also, we frequently use GitOps tools such as FluxCD or ArgoCD that will continuously compare the state of Kubernetes objects with what you have defined in the Git repository. For this reason, you should never use replica property on the deployment or stateful set, because you'll get a race condition. For example, ArgoCD will keep applying one replica, and horizontal pod autoscaler will keep scaling this to 5. Also, to target deployment, in this case, we use a name property, not any labels. Now, if you want to use custom metrics, for example, the number of requests per second, you would need additional component, and I have another tutorial covering this. To use Autoscaler, you need some metrics. We usually deploy a metrics server that would scrape each kubelet and publish those metrics to the metrics.k8s.io Kubernetes API. This component rarely needs any maintenance, so it's safe to use Helm chart to deploy it and forget about it. Also, I'll cover the common pattern to initialize any Terraform provider that needs access to Kubernetes, such as Helm, kubectl, or Kubernetes Terraform providers. First of all, we need to deploy metrics server. For this example, I decided to use Helm and show you how you can initialize Helm provider and deploy any Helm chart to EKS. I'll be using a very common pattern of using data resources to authorize Helm provider. You may see this in many examples. The data resource will also wait until EKS is provisioned, so it's safe to run everything together. To initialize Helm provider, we either use auth token directly, which is in my opinion the most convenient approach, or you can use exec and execute a command to get that token. In the second case, you have to install AWS CLI on the machine where you would want to run Terraform. In the first case, it's not necessary. And if you create a module, you would want to initialize providers in the environment folder, not in the module itself. Now, this is the Helm release resource provided by the Helm Terraform provider. It's very similar to the Helm CLI command that you would run, except you don't create aliases for the Helm repositories, you use them directly. Also, there are a couple of ways to override variables. You can override individual variables using the set block, or you can provide a YAML file with all variables. Additionally, you can use Terraform template built-in function to create YAML template and override some variables in there if you need to dynamically obtain anything. For example, AWS account number or IAM role, ARN, stuff like that. And finally, let's explicitly depend on the node group, otherwise Helm may time out and fail. Next, we need to create metrics server variables that we want to provide or override. It's going to be under values folder. Now, most of it is default, just make sure that you're using the correct port for scraping metrics. Also, in the future, you may want to adjust resolution, unlikely but possible. Alright, since we're using a new Helm provider, we need to reinitialize Terraform. Next, let's go ahead and apply it. Let's check if the metrics server is up and running. You can also try to fetch some logs and make sure that there are no errors. This especially needs to be checked if you're using kops to provision Kubernetes cluster. I don't see any errors, so we can continue. And of course, the most important check is to try to get metrics by using top pods or top nodes command. You may see a message like metrics are not available yet for the first minute or so. If you don't see CPU and memory usage of pods, you will want to carefully check the metrics server logs. At this point, we have verified that metrics are present. Let's go ahead and deploy our example. Now, make sure that your deployment has a resource block and especially check that the requests section, because the horizontal pod autoscaler will use that part, not the limits, to calculate usage in percentage. Next, we have the service object to be able to generate some artificial load. And finally, we have HPA object itself. Make sure you're using the same namespace. To target deployment, we use name property and not labels. Also, set the minimum and maximum number of pods. We can use CPU utilization or memory utilization in percentage. For example, in this case, we want to scale our application if CPU exceeds 80% or memory exceeds 70%. If you want to use custom metrics, I have a dedicated tutorial explaining how to do it. For example, if the application exceeds 100 requests per second, we want to scale it up, or any other custom metrics besides CPU and memory utilization. Let's go ahead and apply it. Check if the sample application is running. Check the HPA object. Keep in mind that if you forget to define the resource block on the deployment object, HPA target will keep showing unknown. In our case, it just needs a few seconds to collect metrics for that pod. We have 15 seconds metric resolution configured on the metrics server, if you remember. Next, we need to get the service name and port forward our application to test it. Alright, let's send a request to generate a Fibonacci number, which is a CPU-intensive task. It will force our application to hit the HPA target of 80%. You can see that the second pod was created to handle the load. Horizontal pod autoscaler will also scale it down after 5 or 10 minutes if there is no load. That parameter is also configurable. And at the end, don't forget to delete that example namespace with the deployment and HPA. That's all for this section. Next, we'll compare 3 different approaches that you can use to authorize your application to access AWS services. We'll compare pod identities with pod OpenID Connect provider and IAM roles for nodes. This is the fifth part of Amazon EKS tutorial. In this section, we'll cover EKS Pod Identities and Cluster Autoscaler. Cluster Autoscaler is external component that you need to additionally install in your EKS cluster to automatically scale up or down your cluster. If you remember, EKS node groups are created as regular AWS autoscaling groups with maximum, minimum, and desired size properties. When Autoscaler detects any pending pods in your cluster, it will adjust the desired size property on the autoscaling group to fit all the pods. Keep in mind, if you created your EKS using Terraform, you may need to explicitly ignore this property in the code. Otherwise, Terraform and Autoscaler will keep updating the same property when you run Terraform apply. Additionally, Cluster Autoscaler needs permissions to interact with AWS and adjust the desired size. So we need to authorize it somehow. Previously, we used OpenID Connect Provider, and it was a bit complicated. You had to create OpenID Connect Provider on the IAM side, then create IAM role and establish trust with a particular namespace and airbag service account. The most annoying part about OpenID Connect Provider was having to use annotation with IAM role IRN on the service account. Now, EKS team has developed a new approach called EKS Pod Identities that we can use to grant access. To enable it, you can use EKS add-on, which is super easy to install. You still need to create IAM role for the Kubernetes service account, but for the trust, you use the same pods EKS Amazon AWS.com. Also, to bind IAM role with a service account, we don't use annotations anymore. Instead, you use EKS API and Pod Identity Association resource. First of all, we need to deploy EKS Pod Identity agents as a daemon set. This agent will run on every single node in your cluster. The easiest way to install it is to use EKS managed add-on. You just need to specify the cluster name, the add-on name, and the latest version. To find the latest version of any specific add-on, you can run the following command: describe add-on versions. The latest version for now is 1.2.0. If you find a new version, just update it in the Terraform code. Alright, let's go ahead and run Terraform. Make sure that the agent is running. I have a single node, so I have only one agent pod. You can also get a daemon set just to check that all agents are running. Without the agent running, you won't be able to authorize your client with AWS services. Next, let's create all necessary components for the cluster autoscaler. First of all, we need a role, and for the trust relationship, you will always use pods.eks.amazonaws.com. When using OpenID Connect Provider, you had to specify the namespace and the service account name under trust policy. Next, we need to create a policy that allows the cluster autoscaler to access AWS Autoscaling group. Then we attach this policy to the IAM role for the autoscaler. Finally, we need to associate this with a Kubernetes service account. You still need to provide a namespace where Autoscaler will be running and the Kubernetes service account name. Next, we need to deploy it to EKS. Let's do this by using Helm chart as well. Don't forget to update the region for the autoscaler. When we used OpenID Connect Provider, we had to add additional annotation and pass it as a Helm argument. I use metric server as a dependency, just to follow tutorial. You can use node group instead to deploy multiple Helm charts in parallel. Let's run Terraform apply one more time. Now, we have the cluster autoscaler running. In case your pods remain in pending state and do not trigger autoscaling, the best place to find an error is autoscaler log. At least for the first time, keep tailing logs and check for any errors. To test autoscaling, we'll use a deployment with 5 replicas, and don't forget to define the resource block as well. Since I have only one node cluster, it wouldn't be enough. Let's watch the nodes. And in the second tab, let's watch the pods. It's time to apply deployment. You can see that only 2 out of 5 pods are being scheduled. Another way to check if your cluster will be scaled up is to describe one of the pending pods. And under the Events section, you'll see the message that the pod triggered or didn't trigger autoscaling. In about a minute or so, EKS should add additional nodes. I have another tutorial that covers Carpenter and KEDA autoscaling. And don't forget to delete this example. In the following section, I'll cover AWS Load Balancer Controller, how to use it to create network load balancers, as well as ingresses, and secure it with TLS certificates. In this lesson, we'll talk about how you can expose your application running in Kubernetes to the internet, or in some cases only within a VPC. When you create a typical service of type load balancer for your application, Kubernetes knows how to create a cloud load balancer, no matter which cloud provider you use. AWS, Azure, or GCP. This task is performed by the Cloud Controller Manager that ships with Kubernetes and contains the logic for creating basic resources in different clouds. When it comes to AWS, for a very long time, it would by default create a classic load balancer. You can use specific annotations to change the type, scheme, and other configurations. However, this functionality is still tied to Kubernetes source code, which means the developer team responsible for that cloud logic must wait and go through the Kubernetes release cycle. As you can see, this is not very convenient and slows down the release of new features. Currently, it is deprecated and only receives security and bug fixes. Another issue with using legacy Cloud Controller Manager when creating a load balancer is that it adds all your Kubernetes workers to the target group and uses node ports behind the scenes to route traffic. This approach adds additional network hop, and if you run very large Kubernetes clusters, there is a hard limit of 500 nodes or so that you can add to the target group. Now, since Kubernetes became incredibly popular, cloud providers started to develop their own controllers to handle the specific cloud logic. For example, AWS has AWS Load Balancer Controller that you can additionally install in Kubernetes, usually using Helm chart. This controller can create load balancers and ingresses, a feature that was never added to the original cloud controller. Since it's a separate project hosted in its own repository, it has independent release cycle. This allows cloud providers to develop new features and quickly release them to the public. One of my favorite features is that since we use the native VPC network when creating EKS cluster, each pod gets VPC routable IP addresses. This means you can directly add pod IP addresses to the load balancer target group. Now, there are two types of ingresses available to you, each with its own pros and cons. For example, when you use AWS Load Balancer Controller to create ingresses, it creates a layer 7 application load balancer. It understands HTTP protocol, and you can use it to route requests based on the host header, HTTP path, or even HTTP verbs such as get and post. As a target group, it directly adds the pod's IP addresses. I should mention that instance mode is still available, but IP mode is more efficient, and we'll use that instead. The logic for routing requests is outside of Kubernetes cluster. For example, when you decide to secure your application with TLS and HTTPS, you need to obtain a TLS certificate from AWS Certificate Manager service and use annotations to attach it. This way, you don't have to keep the certificate and private key inside Kubernetes to terminate TLS. On the other side, we have traditional ingress controllers such as Nginx, Traffic, and many others. All of them are deployed in Kubernetes as regular applications. When you install external ingress controller, it creates a layer 4 network load balancer, which will be the gateway for your application. Each request will go through, in this example, Nginx controller pod, and then be routed to your application. The logic for routing requests is inside the Nginx pod. To secure your application with TLS, you need to deploy Cert-Manager, which automatically updates obtains and renews certificate from Let's Encrypt. Keep in mind that you have to store certificate and private key inside Kubernetes and mount them to the Nginx pod. This way it can terminate TLS and route traffic to your application. Since we have a proxy, it adds complexity, but we can collect Prometheus metrics from a single place for all applications. For example, you can get metrics such as requests per second, latency, availability, and other metrics. With application load balancer, you would need to get metrics from AWS side. Also, when using a traditional ingress such as Nginx, we share a single load balancer across applications inside Kubernetes. If you use AWS load balancer controller, it creates one application load balancer per ingress. There are some workarounds, but in production, you would most likely stick with that approach. In my opinion, you definitely want to install AWS load balancer controller and create a network load balancer for the Nginx ingress controller using IP mode, which we'll do in the following lesson. Alright, let's go ahead and create necessary Terraform components. This controller also needs access to AWS to create load balancers. To grant access, we'll use pod identities as well. In the previous example, we used assume role property on the role itself. In this case, we do exactly the same, but for creating assume policy, we use a data resource. Next, we create IAM role and attach this assume policy to it. The previous example created the same role using a single Terraform resource. This example splits the creation into two objects. Next, we need to create IAM policy for the AWS load balancer controller that defines actual permissions in AWS. Again, there are a couple of ways of doing this. In the previous example, we created a policy using a single Terraform resource. In this case, we will create a JSON IAM policy file and load this policy into Terraform resource. Then we need to attach this policy to IAM role, which will be used by this controller. Finally, we need to link this IAM role with Kubernetes service account, and we'll also deploy this controller to kube system namespace. Alright, we finished configuring IAM permissions, and next we need to deploy controller using a Helm chart. This Helm chart requires EKS cluster name. The Kubernetes service account name must match the one you linked in EKS. Also, let's depend either on the node group or the previous Helm chart. This Terraform file contains all necessary components to deploy AWS load balancer controller to EKS, but we still need to create that IAM policy file. It's going to be under IAM folder. It's pretty large IAM policy and doesn't have any constraints. For example, if you wanted to dynamically add resource constraints, you would probably use template file Terraform function and pass it during creation. I showed an example in the previous section. Now, let's go ahead and apply it. Let's make sure that the controller is deployed and running. For the first example, we'll use a simple deployment and create a service. To use AWS load balancer controller, you need to use load balancer type annotation. Otherwise, in-tree legacy cloud manager controller will be used. I also suggest using IP mode instead of instance mode to avoid routing your requests through the node ports. You can configure it to be public with public IP address and accessible to anyone on the internet, or you can create it as internal, which would have only a private IP address and be accessible only within the VPC. Optionally, you can use a proxy protocol if your application needs to know the actual client source IP address. Otherwise, it will get load balancer source IP. I added a link to all possible configurations available through annotations at the top of the file. That's all the YAML we need for the first example. Let's go ahead and apply it. Let's get the services in our namespace. It may take a few minutes for the load balancer to show up under external IP. If it's not there, check AWS load balancer logs. You may have misconfigured permissions, and the controller may not be able to provision load balancer in AWS. Let me show you this load balancer in the console. You can see this load balancer, but it is still in the provisioning state. Usually, it takes a couple of minutes for the load balancer to transition to the active state. Under Details, you can see that it is a network load balancer, which means it's a layer 4 load balancer. It's a little bit cheaper and faster than application load balancer provided by AWS. Also, if you used the legacy Cloud Manager controller, it would provision a classic load balancer. Under the scheme, you can see that it is internet-facing, so anyone can access it. Just a heads up, don't use internet-facing load balancer to expose your internal services and dashboards, such as Prometheus and Grafana. In the first section of this tutorial, we created a VPC with subnets and used special EKS tags to inform EKS where to provision public load balancers. You can see that both of those subnets are public. Now, let's refresh it one more time. Now it's active, which means it's ready. Let me show you one more thing. Under Listeners, you can open the target group that is used by our load balancer. You'll find that since we used IP mode for the load balancer, it does not add all the Kubernetes nodes to the target group. Instead, it added a single pod IP address. This is the biggest advantage of using IP mode. There is no restriction on how many nodes your Kubernetes cluster can have. As far as I remember, if you use a classic load balancer, it will create a node group out of all EKS nodes, and it can only add a maximum of 500 nodes. Also, let's wait until the health status is healthy. Don't test your load balancer until you verify all these details. Let me get the pod IP just to prove that the target group is using this IP address. Now, we can use curl and hit the load balancer. Alright, it works, and we got the version back from our application. That's all for the first example. Let's delete this namespace. In addition to creating load balancers, this AWS load balancer controller can create ingresses. It ships by default with ALB Ingress class. In the following example, we'll create a plain ingress to expose our application. We have the same deployment object. Then we have a service of type cluster IP. If you want to create ingress using instance mode, not IP mode, instead of cluster IP, you would use node port even in the cloud. Then we have ingress resource. The important part here is that our application should have a health check that returns a 200 status code. We also have the same internet-facing value as well as IP mode. Now, to test this ingress, you can use exactly the same host. We're not going to create a DNS record for this example, and I'll show you how to test it locally. That's all for the ingress. Let's apply it. Get ingresses in our namespace. Again, it may take a few minutes for the load balancer to show up here. Let me open this application load balancer that was created by the ingress resource. You can see under load balancer type that it is application load balancer. Application means it understands HTTP and can route traffic based on HTTP path or a verb such as get, post, etc. It is also created in the public subnets. Alright, let's wait until it's provisioned. Now, under the listener, you can find a rule with a pod IP. You can see that the target is pod IP address. If you had more pods, you'll get more IP addresses here. It's healthy because our health check returns 200 status code. Now, let me show you how to test it without creating DNS. This is actually a very useful technique even in production if you want to test your application before changing DNS record and sending live traffic to it. To test, you can use a header with our host. Keep in mind, since it's Ingress, we don't need to use port 8080 anymore as we did with the load balancer. Alright, it works. Let's delete this example as well. For the final example in this section, we'll need a TLS certificate to secure our Ingress. For the application load balancer, we cannot use Let's Encrypt and need to obtain a TLS certificate from Cert-Manager, a managed AWS service. You can do this even if you host your own domain outside of AWS. But in my case, I use Route 53, and most likely you would do the same. Now, we need a public certificate. Here you would provide your domain name. You can add additional names below as well. For example, if you have devopsbyexample.com and www.devopsbyexample.com, you would need to put 2 domain names here. Next, we select DNS validation and use default RSA key type. Now, we have created the certificate request. Next, we need to prove that we own our domain. In the case of DNS validation, we need to create a couple of CNAME records for each domain on the certificate. If you host your domain in Route 53, it's very easy. Just click the Create Record button and it will be done automatically for you. Now, we need to wait a few minutes until DNS is ready and AWS is able to verify it. Let me go to Route 53 to show you the records that I have and the one that was created to validate ownership. Down below, I have a record to validate certificate. Let's refresh one more time and it looks like the certificate was issued. To be able to use it, we need to copy certificate IRN and paste it into Ingress. Alright, this is the third example for this section. We have exactly the same deployment and service object. The difference is here. We need to replace this IRN with our new certificate. The next annotation is to configure redirect from port 80 to port 443. This basically means if anyone tries to access our application using HTTP, they will be immediately redirected to HTTPS. It's a very common redirect, so I suggest you keep it unless you have a specific requirement. It will be public as well, IP mode and the health check. You may notice that this Ingress does not have a TLS section. It's because TLS will be terminated outside of the Kubernetes cluster on the application load balancer. So there is no need to keep certificate and private key inside Kubernetes. This is very different from the Nginx Ingress controller that we'll discuss in the next section. Also, in order to use AWS load balancer controller to create Ingress, we need to specify its Ingress class name. A long time ago, we had to use Ingress annotations. Now it's done through the special Ingress class name property. Alright, we can apply it now. Let's get the Ingress. To test this Ingress, we can create a DNS record. But before we do that, let's wait until the application load balancer is provisioned. Also, let's check if the pod is healthy under the target group. Now we can create a DNS record. It's going to be a CNAME record, and for the value, we'll use load balancer DNS. Let's wait a few minutes and check if we can resolve DNS for our application. The final test is to make sure that we have a valid certificate in the browser. it looks like the connection is secure and we have a valid certificate which was issued for a year. When using Let's Encrypt, your certificate's valid for 90 days and automatically renewed every 60 days. Alright, let's delete this example. In the next section, we'll do pretty much the same, but we'll use Nginx Ingress controller and additionally install Cert-Manager to obtain certificate. I'll also cover the differences and share my opinion on which controller you should use and why. This is the 7th part of Amazon EKS tutorial. In this section, we'll talk about Nginx Ingress controller. First, let's take a look at the high-level architecture. When you install Nginx Ingress controller in your cluster, it also creates a layer 4 network load balancer in the cloud. This load balancer will be used to route every single request sent to your application using this particular Ingress class. The network load balancer does not understand HTTP protocol and will not terminate TLS. It will pass everything to the Nginx controller itself. When you create Ingress object to expose your application, that object is parsed and converted by the controller into the native Nginx configuration. So when a request comes from the load balancer, Nginx will act as a reverse proxy and based on the routes defined in Nginx, route the request to your specific application. Since we'll use AWS load balancer controller to create network load balancer for the Nginx Ingress controller, we'll use IP mode. This means AWS will not use node ports and add all your Kubernetes workers to the target group. Instead, it will use Nginx controller pod IP addresses only in the target group. This helps avoid some limitations, removes additional network hop, and increases performance. So I suggest installing AWS load balancer controller before deploying Nginx Ingress controller. Now, since we have a middleman such as Nginx proxy, we can collect many metrics for each destination application without additional effort. You can scrape Nginx Prometheus metrics and create dashboards with latency, request per second, availability, and other metrics. I have another video that explains how to monitor any application that uses Nginx Ingress controller. In large companies, it's very common to deploy a public-facing Ingress controller that uses external load balancer with a publicly routable IP. You would use that Ingress to expose client-facing applications. On the other hand, you would deploy another Nginx Ingress controller with only a private load balancer. This load balancer will get a private IP that is only routable within your VPC. You would use it for your internal services as well as internal dashboards such as Grafana. We frequently use this type of ingress with private Route 53 hosted zones and client VPNs for the dashboards. I'll create additional video explaining how to use private ingress with private DNS and client VPN to securely expose dashboards only within your team. Another benefit that not many people know is that you can use Nginx Ingress controller to route custom TCP and UDP services. Usually, we would expose them with a service of type load balancer, resulting in as many load balancers as you have services. Nginx Ingress controller allows sharing a single load balancer to expose all your custom services. This is mostly used because load balancers have hourly charges. So by limiting the number of load balancers, you reduce the cost of your infrastructure. I also have a video explaining how to do this using Nginx config map. In the majority of cases, you want to secure your application's HTTP endpoint with a TLS certificate. It is possible to provide your own certificate and private key to the Nginx as a Kubernetes secret, but in most cases, we want to automate this process. To automate, we deploy additional component called Cert-Manager. It integrates with Nginx Ingress via annotations and automatically obtains and renews your certificates. If it fails to renew the certificate, you'll get a warning via email from Let's Encrypt ahead of time, giving you a chance to debug and fix the issue. To obtain certificate, Cert-Manager uses a custom resources. First, it creates a certificate and checks if you already have a certificate for that domain. If not, it creates a certificate request custom resource. Behind the scenes, it generates a private key and stores it in Kubernetes secret. Then Cert-Manager will create another custom resource called an order. Finally, the order custom resource will create a challenge. There are two main challenges that you can use. HTTP 01 is the simplest one to configure. Cert-Manager will obtain a secret token from Let's Encrypt and expose it on a custom path on your domain. Then Let's Encrypt will verify it and issue a certificate. Another challenge, DNS 01, is a little bit more complex to configure because you need to grant Cert-Manager IAM permissions to create TXT records in Route 53. However, it is preferred in production because it allows you to get a certificate even before routing and changing live DNS to point to the Nginx Ingress load balancer. With DNS01 challenge, Cert-Manager will get the same secret token, but to prove that you own the domain, Cert-Manager needs to create custom TXT records. When Let's Encrypt can query your domain and verify those records, you'll get a certificate. Certificates are valid for 90 days, but approximately every 60 days, Cert-Manager will try to renew them. There are two main reasons for the short expiration on the certificate. If the certificate is compromised, attackers would have a limited amount of time to cause damage. Another reason is that short interval forces you to automate this process instead of manually updating certificates. I have another lesson explaining how to debug both DNS and HTTP 01 challenges. Alright, let's create all necessary components to deploy Nginx Ingress controller. It doesn't need any permissions on AWS side. One of the most common deployment methods is to use Helm, so let's use open source Helm chart and override a few variables. Let's create Nginx ingress.yaml file. In the past, we had to use both the Ingress class and the legacy annotation so that Cert-Manager could create Ingress to validate HTTP 01 challenge. This is no longer necessary after Cert-Manager was updated to use Ingress class name property as well. Usually, you would have external ingress that exposes applications to the internet as well as internal ingress with private DNS to expose some internal dashboards, such as Grafana or even Prometheus. So let's give this ingress the class name external Nginx. Then we can configure the load balancer that we want. We'll use AWS Load Balancer controller to create a network load balancer for the Nginx Ingress because we want to use IP mode. I covered everything related to AWS Load Balancer controller in the previous section. Finally, we want this load balancer to have a publicly routable IP address. That's pretty much all for the deployment. Let's go ahead and run Terraform. Now, let's get the service. Nginx Ingress will use this load balancer for each application that you configure with this ingress. You will always want to create a CNAME record with a value pointing to this load balancer. By default, it exposes only ports 80 and 443. There are some options to expose custom TCP and UDP services using a single load balancer, which is useful for those who want to save on load balancer hourly charges. As you can see, it's a network load balancer and it's public. Let's wait until it's active. Let's also open the target group to make sure it uses IP mode and routes traffic directly to the Nginx Ingress controller. Let's also wait until the controller shows up as healthy in the console before testing anything. So this is Nginx Ingress controller pod IP address. If you get more replicas, you get more IPs here. You can see that IP of the pod matches the IP in the target group. The load balancer will always route traffic to your application through Nginx Ingress pod, because all the logic is inside Nginx, not in the load balancer, like with AWS Load Balancer Controller. After deploying Nginx Ingress, we have the second Ingress class, external Nginx. The first one we used in previous section. Now, let's go ahead and test. For the first example, we'll use a simple deployment object with a service cluster IP. For the ingress, we'll use a simple ingress resource that routes traffic based on the host header in the request. You can keep this host because we're not going to create a DNS record. We'll use curl and provide the host to test. For the next ingress, you will need to create a DNS record. Also, to use Nginx Ingress, just use ingress class name property and match the service and the port number. Alright, let's apply it. Let's get the ingress. It may take a minute or so to populate the address section. You can wait or just create a CNAME pointing to the load balancer. It's going to be the same value. Let's get the ingress one more time, and now we have the address. This ingress only uses HTTP protocol and port 80. Now, to test it locally without creating a DNS record, you can pass the host header to curl, and the following argument will be the load balancer hostname. Alright, it looks like it works, and we get the version back for our application. By the way, the source code for this app is in the repository as well. It's a very simple Go application. Alright, let's delete this namespace with all resources. For the next example, to use HTTPS and issue a certificate from Let's Encrypt, we need to additionally install Cert-Manager. In this lesson, we'll use HTTP 01 challenge to prove ownership. In one of the previous videos on how to debug Ingress, I covered both DNS and HTTP challenges and which one you should use in production. We'll use a Helm chart as well to deploy it to our cluster. Cert-Manager uses custom resources to automatically obtain and renew certificates, so we need to install them during the deployment. Alright, let's apply Terraform. Let's get the pods to verify that all of them are running. Now, for this example, we need to create a cluster issuer that you can use in all namespaces to obtain certificates. You need to update email so that if Cert-Manager fails to renew a certificate, you get a warning ahead of time. Also, for this lesson, we'll use HTTP 01 resolver and use our ingress to resolve those challenges. Take a note of the name property. We'll use it in the ingress annotation to reference this issuer. Then we have the same deployment and the service objects. Finally, the ingress. First of all, we want to use our Cert-Manager cluster issuer for this ingress. To secure this ingress with HTTPS, we need additional TLS section. You should include all DNS names that you want to use and the secret name within this namespace for the certificate and the private key. It will be automatically mounted to the Nginx Ingress controller, enabling it to terminate TLS and route requests to your application. That's all, let's apply it. Now, it's time for me to show you how to debug Ingress. First, we need to check if the certificate is ready. As you can see, this one is not. So the next step would be to describe it. You'll find that certificate created certificate request custom resource, which behind the scenes generated a private key and stored it in the Kubernetes secret specified in the Ingress resource. Let's go ahead and describe that certificate request. Certificate request created another custom resource called order. Let's describe that as well. The order created the last custom resource that we need to investigate, which is called challenge. In our case, it's HTTP 01 challenge. Let's describe it. Here you can see the problem. We created the ingress, but never created a DNS record, so that Let's Encrypt can verify that we own this domain. Solution is very simple. We just need to create a CNAME record pointing to the Nginx Ingress load balancer. But before that, let me show you a couple of things. Cert-Manager also created additional temporary ingress to expose the token provided by Let's Encrypt. Alright, let's create a CNAME record. You can do this with any DNS host provider. In my case, I use Route 53. This time, you need to use your own domain. The type will be CNAME and the value is the load balancer hostname. After you create a CNAME record, it may take a few minutes to obtain a certificate. So let's watch and wait. Alright, we have the certificate now. For the final check, let's verify in the browser that the connection is secure and we use the Let's Encrypt certificate. You can see we have the certificate, which is valid for 90 days, and approximately every 60 days, Cert-Manager will try to renew it automatically. If it fails for some reason, you'll get a warning at the email address you used to create cluster issuer. Alright, that's all. Let's clean up. In the next section, we'll talk about how to run stateful applications in EKS and use CSI driver to allocate EBS volumes and mount them to the pods with ReadWriteOnce access mode. This is the 8th part of Amazon EKS tutorial. In this lesson, we'll talk about storage and how to run stateful applications in EKS. Now, if you try to deploy a stateful set in EKS right after you provision a cluster, your pods will be stuck in pending state. And if you describe the persistent volume claim, you'll find that the driver or provisioner is missing. To allocate a volume from one of the cloud storage providers, such as EBS, you need to additionally install something called CSI driver. CSI or Container Storage Interface is a Kubernetes extension that allows storage vendors to integrate with Kubernetes. With CSI, storage vendors no longer need to write code in Kubernetes itself. This interface allows them to develop storage plugins independently and deploy those drivers to Kubernetes using Kubernetes primitives, such as Kubernetes pods. One of the most common storage providers people use in AWS and EKS specifically is EBS, Elastic Block Storage. It's one of the cheapest options and very reliable. By default, EKS ships with a default storage class called GP2. You can use it with ReadWriteOnce access mode, which allowing mounting EBS volume to a single pod. Well, technically it's a single node, but you should only rely on it if you have a specific requirement and have pod affinity property on your stateful set. It's very common to increase the size of the disks for your EC2 instance. For example, when you run a stateful system like Kafka. To allow expansion of EBS volumes attached to Kubernetes nodes, you need to create a custom storage class. I suggest using GP3 storage class and explicitly allowing expansion. In this case, you still won't be able to change the stateful set template because it's immutable property, but in emergency you can manually edit persistent volume, and in a few seconds the CSI driver will increase the volume. I use this feature with Prometheus and Thanos deployments. In the following video, we'll use EFS file system. It's elastic, meaning you don't need to manually increase the size, and it supports ReadWriteMany access mode, allowing you to mount it to multiple pods at the same time. Let's go ahead and deploy EBS CSI driver. First of all, we need to create a trust policy, since we'll use EKS pod identities to grant necessary permissions. Then we'll create IAM role using this policy. When it comes to permissions, we can use AWS managed EBS CSI driver policy. It will allow to allocate EBS volumes and attach them to Kubernetes worker nodes. Optionally, if you want to encrypt your EBS volumes, you can create the following IAM policy. I think many companies would like to encrypt their data at rest. Next, we'll attach this encryption policy to our role. And finally, we need to associate this IAM role with Kubernetes service account in kube system namespace. We've done this a couple of times already, so you should be familiar with this process. To deploy, we can use managed EKS add-on. It's pretty much the same as a Helm chart, just wrapped and tested by AWS. The add-on name is AWS EBS CSI driver. You can use a similar command EKS add-on describe to get the latest version of this add-on. Alright, let's go ahead and install it. To test, I have prepared a stateful set which will allocate as many persistent volumes as you have replicas. The test is simple. If we can deploy stateful set successfully, it means we have configured everything correctly. Let's try to get the pods. Keep in mind that if you don't deploy CSI driver, all your pods will be stuck in pending state. In this case, it just takes a few seconds to attach a volume to Kubernetes node. Let's get the PVC, which is the persistent volume claim, and it looks like it's already bound. Let's describe it to make sure it was successfully allocated. These are pretty much the same steps you would follow if your pod is stuck in pending state. Alright, we just verified that we can run stateful applications using CSI driver. The next section will cover how to use EFS elastic file system, which you can mount to multiple pods at the same time with ReadWriteMany access mode. This is the 9th part of Amazon EKS tutorial. In this section, we'll talk about EFS file system. Now, let's go over some main features of EFS. First of all, it's elastic, meaning you don't need to worry about capacity ahead of time. This file system will scale automatically when you add or remove files. When you create a persistent volume claim or stateful set template, you no longer need to provide storage capacity ahead of time. Although Kubernetes requires us to specify the size of the volume. Since we use EFS, that size doesn't mean anything. Second, you can use ReadWriteMany access mode and mount the same volume to multiple pods at the same time. When one pod writes data to that volume, the other one will immediately see that file. Third, it's much more expensive than regular EBS volumes, so keep this in mind. To integrate this file system with EKS, we first need to create EFS file system in AWS. Then we need to create mount targets in all availability zones where we deploy our Kubernetes workers. We have two private subnets in two different availability zones. So we need to create two mount targets. Additionally, since it's a network file system, we need to use EKS security group to allow Kubernetes workers to connect to the EFS file system. Finally, we will create Kubernetes storage class and use the EFS storage class to allocate volumes using persistent volume claims or stateful set volume templates. At this point in time, EFS CSI driver doesn't support EKS pod identities. In the future, they will most likely update AWS SDK that they use, but for now you have only two options. Either attach all permissions to the Kubernetes nodes, or the better option is to use OpenID Connect provider and link Kubernetes service account with IAM role. I think it's a good thing. And I can cover both approaches that you can take to authorize your application with AWS services. Alright, first of all, we need to extract certificate from EKS Cluster and use it to create OpenID Connect provider on AWS site. That's all you need to create this provider. Next, let's create EFS file system in AWS. There are a few configurations that you can change, but we'll mostly keep all the defaults. Next, we need to create a mount target in each subnet where we deploy our Kubernetes workers. Additionally, we need to open a firewall for those workers to connect to the file system. In our case, we'll use EKS security group that was created by EKS itself when we provisioned the cluster. Now, since we created two private subnets in the first section, we need to create another EFS mount target in the second private subnet. At this point, all Kubernetes workers will be able to connect to EFS file system. The next part is to grant all necessary permissions for the EFS CSI driver to attach volumes to our worker nodes. Because we use OpenID Connect provider, we need to create a trust policy and specify EFS CSI driver Kubernetes service account and the namespace where we will deploy it. Then create IAM role and attach this trust policy. Now, AWS manages one IAM policy for the EFS driver, so let's use that. Finally, we need to deploy it using a Helm chart. You need to specify the service account name, and most important part is to link Kubernetes service account with AWS using IAM role IRN annotation. In this case, we can dynamically pass it using a Terraform resource reference. Now, we need to initialize Kubernetes provider and use the same data resources that we used before to initialize Helm. So I leave it here for the reference. We'll use this new Kubernetes Terraform provider to create a custom Kubernetes storage class that uses EFS file system. Alright, let's go ahead and initialize Terraform because we added a new provider. Then let's apply it. Let's get the pods and verify that EFS drivers are running. Since EFS is a little bit more complex to configure, I would suggest tailing driver logs to check for any errors when you deploy a stateful application. Now, let me show you in AWS console how EFS file system looks like. Under the Network tab, you can find two mount targets that we created. And don't forget to use your security group, otherwise your CSI driver will time out while allocating EFS volume for the Kubernetes pod. To test, I have prepared a single persistent volume claim with ReadWriteMany access mode that will attach to two different pods. We use EFS storage class, and even though EFS is elastic file system, Kubernetes requires us to put something under storage, so let's use 5 GB. Finally, we have two pods that use the same MyApp persistent volume claim. It is possible because it supports ReadWriteMany. Okay, let's apply it. You can see that both pods are running, which means we were able to attach the single EFS volume to both pods. In the next part, I'll show you how to use AWS Secrets Manager to mount secrets as environment variables and files inside the pod. We'll mount them as JSON objects as well as parse it and only mount the values. This is the final 10th part of Amazon EKS tutorial. In this lesson, I'll show you how to integrate AWS Secrets Manager with EKS. Secrets Manager is used to securely store credentials such as passwords, API tokens, usernames, and similar data. First of all, we'll create a username and a password in AWS Secrets Manager like this. By default, if you want to use this set of key value pairs and mount them to the pod, you'll get a single JSON object, which is not what most applications would expect. In this video, I'll show you how to parse each value and mount them as environment variables, such as my password and my username, to the pod inside Kubernetes. Additionally, I'll show you how to mount the same secrets as files so that your application can read those files during startup. First of all, we need to install generic store CSI driver that would integrate secrets with many different cloud providers. This CSI driver, which stands for Container Storage Interface, meaning those secrets will be mounted as Kubernetes volumes. But don't worry, I'll show you how to use those secrets as environment variables as well inside the container. That's why we need to explicitly enable it in the Helm chart. This will create additional airbag policies needed to use environment variables. Next, we need to install a cloud-specific provider. In this case, of course, we need AWS. You can use GCP, Azure, and some other providers also available. Since EKS pod identities are still new and not supported by all Kubernetes extensions, let's use old OpenID Connect provider, and first we need to create a trust policy. This trust policy is used not by the CSI driver itself, but rather the application that needs access to a specific secret. So in this case, we'll create a trust policy for the sample application that we'll deploy later. It will be deployed in the 12th example namespace, and the Kubernetes service account will be my app. And the next step is to create IAM role for that specific application. Let's call it my app secrets and use EKS name as a prefix. Next, we need to grant access for this application to a specific secret in AWS. Just to simplify this tutorial, I'll use a wildcard, which you should never use in production. You should only grant access to a specific AWS secret using its IRAN. Then we need to attach this policy to the application IAM role. Finally, we need the role IRN to link AWS IAM with Kubernetes service account. You can automate this by using Kubernetes provider or by passing the IRN as a Helm argument. I showed an example in the previous section. Alright, let's go ahead and apply Terraform. The next step is to create a secret in AWS Secrets Manager. Click on Store a new secret. Select Other type of secret. For the first key, let's use username, and for the value, you can provide arbitrary string. For the second key, let's use password. Keep those secrets exactly the same, because we're going to parse them next. Let's call this secret my app secret v3, because I already created a couple of them for testing. Then click Store. That's going to be our secret name, but for the permissions, you need to use IRN of that secret. For this example, it's important to follow the same naming, since we authorized the Kubernetes account only in this namespace. Next, we need to create secret provider class. You need to place it in the same namespace and region. Then, for the object, use the secret name. If you want to parse and mount values instead of JSON object with the secret, you need to use James path and select the keys that we specified in AWS Secrets Manager. To mount those secrets as environment variables, you also need to create a secrets object and reference those keys from the previous section. I intentionally use different names and aliases to be clear about which key to reference. Next is a very important part, linking this Kubernetes service account with IAM role using this annotation. You can get this IRN from the Terraform output or copy it from the AWS console. Finally, for the deployment itself, you must use the service account with annotation. Now, you can mount your secrets as regular files inside the container like this. Files named username and password with corresponding values. You can also mount those secrets as environment variables. It's up to you, whatever is easier. I personally prefer environment variables. At the bottom of the deployment, you need to create a volume from the secret class that we created earlier. For the first time, to catch any errors, try to follow the driver log. If you have permission errors, you'll see them here or inside other AWS provider that we also deployed. Now, let's go ahead and deploy our application. Let's get the pods. To verify if you have secrets, let's SSH to the pod using the following command. First, let's try to print the value from the username file, and the value is my actual username. Then, let's try the password file, and we have DevOps123. For the environment variables, you can use env command to get all of them inside the container. So we have my password variable as well as my username. In the next lesson, I'll try to cover topics that you send me during the release of this playlist. Thank you for watching, and I'll see you in the next video.